lesson 5 on power system analysis course. In this course, we will talk about the transmission line capacitance. Before we get into the calculation of transmission line capacitance, I would like to answer those questions that I asked in lesson 4. The first question was, why bundle conductors are used in EHV lines? Well, the answer to this question is bundling of conductors, that is, instead of using one single conductor, use of a number of conductor connected by conducting frames reduces electric field strength on conductor surface, which in effect reduces the corona losses, which result in power loss as well as radio interference and audible noise in the system. Bundling also increases the effective radius of the conductor and thereby reduces the inductance of the transmission line. This in effect will improve the regulation of the transmission line. As seen from here, the effective radius for a 3 conductor bundle which are spaced at a distance d from the center or d from each other with a radius r is given by 9th root of r dash into d whole cube, which is equal to cube root of r dash d square. This is much larger than r dash, which is used when a single conductor is used, and therefore bundling helps in reducing the inductance as it increases the effective radius. Second question was, what is transposition? Well, transposition means exchanging the position of the 3 phase conductors along the length of the line. That is, when we have 3 phase conductors which are not equilaterally spaced, that is, equal spacing between them is not possible due to physical constraints of the transmission line construction. That in such a case we will get unequal flux linkages with the 3 conductors. Most of the time, if you have seen the power line transmission towers, you will find that the 3 phase conductors are either placed in a horizontal configuration if it is a single circuit line, or they may be placed in a vertical configuration if it is a double circuit line. Therefore, the equilateral spacing is not there and the distance between the conductors, phase conductors, are not equal. This results in difference in flux linkages with the 3 conductors, resulting in difference in inductances. In order to have a balanced 3 phase system, what we do is we make these conductors, phase conductors, go through all the 3 positions. That is what we do in transposition. We exchange the position of the 3 conductors along the length of the line, so that each conductor or each phase conductor is in all the 3 positions for equal length of the line, which means that the average flux linkage of all the conductors or for all the 3 phase conductors are same. So, if the spacing between 3 conductors are unequal flux linkages will occur when the 3 phase conductors are, even when the 3 phase currents are balanced. Here we show the transposition. The phase conductor A is in position 1 for 1/3 length of the line. It occupies position 2 for the next 1/3 length of the line, and position 3 for the last 1/3 portion of the line. Similarly, phase B conductor is in position 2 for 1/3 of length of the line. Next 1/3 length of the line it is in position 3, and the last 1/3 length of the line it is in position 1. In this way, each phase conductor is occupying all the 3 positions, which results in average flux linkages to be equal. So, we say that by transposition each phase conductor occupies the 3 positions for 1/3 length of the line. Therefore, the average flux linkage and inductance become equal. The third question was how the effect of earth return current is taken into account in inductance calculation. Well, J.R. Carson in his paper in 1923 said that the earth return currents can be taken into account by means of considering earth return conductors. That is, we assume imaginary conductors which are placed below the ground. These conductors are supposed to have the same radius or the GMR as the overhead conductors, and they are placed directly below them in the ground. The distance between the overhead conductor and these imaginary conductors is given by the distance dE, where dE is given by an empirical relation 658.5 square root of rho by F, where rho is the earth's resistivity. Normally, if earth's resistivity is not known, then we assume it to be around 100 ohm meter, and F is the system frequency. So, having answered these questions, now we will go into the main part of the lesson 5. Now, this lesson, as I said earlier, we will be talking about transmission line capacitance and its calculation. So, here we will first start with electric field and voltage calculation. Next, we will take up the transmission line capacitance calculation for a single phase line with solid conductors. Then we will take up 3 phase line with equal spacing, and finally, we will talk about 3 phase line with bundle conductors and unequal spacing. Well, as we have learnt in the lesson 3 and 4 about calculating the resistance and inductance of the transmission line, the transmission line also has capacitance. This is mainly because the line conductors have a voltage difference between the phases, that is, phase conductors have a voltage difference, and there is a difference of voltage between the phase conductor and the ground, and these conductors are separated by a dielectric medium. For overhead line, this is air, and in case of cables, this can be some kind of a dielectric which can be impregnated paper, or it can be XLPE, that is cross linked polyethylene insulation, or some other kind of insulation. Therefore, we have 2 conductors at different voltages, and there is a dielectric between them, which results into a capacitance between the conductors, or between the conductors and the ground. Now, for calculating the transmission line capacitance, we have to go through first using Gauss's law to calculate the electric field strength. Once we have calculated the electric field strength, we find out the voltage between the conductors, and then we find out the capacitance by the relationship C is equal to Q by V. So, we will start with the Gauss's law and calculation of electric field strength. Well, Gauss's law states that total electric flux leaving a closed surface is equal to total charge within the volume enclosed by the closed surface, which basically leads to the statement that normal electric flux density integrated over the closed surface will be equal to the charge enclosed by this closed surface. Mathematically, we can write this as the surface integral over the closed surface of electric flux density d, or the electric flux density which is normal to the surface, into ds will be equal to, or integrated over the surface will be equal to the will be equal to the surface integral of epsilon E, which is again normal to the surface, into ds, that is over the whole surface. Now, this epsilon is the permittivity of the medium and E is the electric field strength at the surface. So, that is what we have done is electric flux density d is replaced by epsilon E, because d is equal to epsilon E that we know from electric field theory. So, this is equal to the total charge enclosed by the volume enclosed by this closed surface. This we can see in this figure very clearly. Let us say we have a conductor which is of a very long conductor of radius r, and this is charged with q coulombs per meter. Here we have assumed q to be a positive charge, it can be positive or negative, it does not matter. So, here we have assumed this conductor of radius r is having a charge of q coulombs per meter, and it is a very long conductor. Now, since this is a perfect conductor, electric field inside is going to be 0. Now, for finding out the electric field outside the conductor, what we need to do is we take up a concentric cylindrical volume of 1 meter long length. So, this volume shown here, this is a concentric cylinder of 1 meter length at with a radius of x. Okay. Now, since the electric field lines will be radial to this surface which is of this concentric cylinder, therefore, there will be no tangential component of the electric field. Now, we can find out with this what is the field strength at the surface of this concentric cylinder. Now, using Gauss's law, we will use the integration, surface integration of epsilon E ds. So, epsilon E x, that is the field strength at this surface of this concentric cylinder, integrated over this closed surface. The closed surface area is going to be equal to twice pi x into 1 meter length of this cylinder. So, epsilon E x into twice pi x into 1 is equal to the charge enclosed, which is q into 1 meter length of the line, because q per meter, q coulomb per meter is the charge on the conductor. From this, we can calculate the electric field strength at the surface of the concentric cylinder of radius x. So, E x is equal to q by twice pi epsilon x volt per meter. Now, using this E x, or the relationship for the field strength at any point, we can always find out the voltage difference between 2 points. So, if we want to find out the voltage difference between 2 points P 1 and P 2, which are at a distance d 1 and d 2 from the center of the conductor, what we need to do is integrate from d 1 to d 2 of E x over d 1 to d 2. So, E x the integral E x to E x dx from d 1 to d 2 will give me the voltage difference V 1 2. So, V 1 2 is equal to integral d 1 integral of q by twice pi epsilon x dx from d 1 to d 2. This is equal to q by twice pi epsilon log n d 2 by d 1 volts. Here epsilon is, as I said earlier, is the permittivity of the medium, and this is equal to epsilon r into epsilon 0, where epsilon 0 is the permittivity of the free space, and for air also it is almost the same. Epsilon 0 is equal to 8.854 into 10 to the power minus 12 farad per meter. Now, we will take, since we have now found out the electric field strength and the voltage between any 2 points for any charged conductor, we can extend it to a multi-conductor system. Now, let us say that we have a system of n conductors with any conductor k having a radius r k and has a charge q k per meter length of the conductor. Then we can find out the voltage between two conductors I and j due to charge on this conductor k. We write this as V I j k, that is voltage between conductor I and j due to charge on conductor k. This will be equal to q k by twice pi epsilon log n the distance d of k to j and divided by distance of k to I, as we can see using the old relationship that we have found here, q by twice pi epsilon log n d 2 by d 1. Now, if we want to find out the voltage difference due to charge from all the conductors which are in this system, then what we need to do is use the superposition theorem, that is add the voltages due to the charge from each of these conductors. So, V I j in that case due to charges on all the conductor will be equal to summation k is equal to 1 to n of q k by twice pi epsilon log n d j k by d I k volts. So, this way we can find out the voltage between any two conductors or any 2 points due to charge on various conductors in a multi-conductor system. Now, let us try to apply this to find out the voltage and then the capacitance of a single phase line. Let us say we have a single phase line with two conductors, conductor x and conductor y. Conductor x has a radius r x and has a charge q coulomb per meter. Conductor y has a radius r y with a charge of minus q coulomb per meter, because conductor y will be the return conductor. So, it will be carrying the return current. So, the charge will be negative of the charge on the conductor x. So, now we using the same formula we can find out V x y will be given by 1 by twice pi epsilon q log n d y x by d x x, that is, because of the charge on this conductor, the voltage difference between these two will be given by this relationship 1 by twice pi epsilon q log n dy x by dx x, and the voltage between these two conductors, that is V x to V y. So, V x y will be equal to minus 1 by twice pi epsilon minus q log n dy y by dx y. So, this can be reduced to q by twice pi epsilon log n dy x into dx y divided by dx x into dy y. That is, this minus is converted to plus by reversing these dxy and dyy, that is taking the inverse of this. So, we get dyx into dxy divided by log n dxx by dyy. So, finally, we get the voltage between two conductors by the relation q by twice pi epsilon log n dyx into dxy divided by dxx into dyy, which if we substitute the values, we get Vxy is equal to q by pi epsilon log n d by square root of Rx Ry, because this would have become d square and this would be Rx Ry. So, this square is taken out, that becomes 2 into q and this 2 pi epsilon. So, this 2 will cancel out and we get finally q by pi epsilon log n d by square root of Rx into Ry. Now, once we have found out the voltage, we can find out the capacitance very easily. Capacitance C x y, that is capacitance between the two conductors x and y, is equal to q by voltage between the two conductors. So, this will be equal to pi epsilon divided by log n d by square root Rx Ry. That is, what we have done is divided q by this term and then we get this C x y is pi epsilon divided by log n d by square root of Rx Ry. So, this, if we consider the radius of the two conductors to be equal, then Rx will be equal to Ry, and therefore, square root of Rx into Ry is equal to R. Therefore, we can write Cxy is equal to pi epsilon divided by log n d by R farad per meter. This is a line capacitance between line to line. Now, if we see this system, in the center of this we will get 0 voltage, because this will be a positive potential, this will be equal negative potential. So, by symmetry at the center we will get a 0 potential or the potential of the ground or the neutral. Therefore, we can find out the voltage to the neutral as Vxn is equal to Vyn is equal to Vxy divided by 2. This will be half the voltage, because the voltage of one conductor is positive, another conductor is negative. So, the 0 potential line will be in between at the half. So, Vxn is equal to Vyn is equal to Vxy divided by 2. Therefore, we can find out the capacitance to the neutral or capacitance to ground as Cn, which will be equal to Cxn and which will be again equal to Cyn, that is capacitance from to ground for conductor X will be same as capacitance to ground for conductor Y, and this will be equal to q by V x n, which is equal to 2 times C x y. As we can see here, between x and y we have a capacitance C x y, and if we have taken the neutral at the center, then we have now capacitance C x n between x and n, and capacitance C y n between n and y, and these capacitances will be equal to 2 times the capacitance between x and y, because they are in series. So, 2 x y and 2 C x y and 2 C x y in series will give me C x y. So, C y n or C x n, which is equal to C n capacitance to ground for any conductor of the for any of the two phase conductor, will be equal to 2 times C x y. This is equal to twice pi epsilon divided by log n d by r farad per meter for line to neutral capacitance. Now, we will take up the case of a 3-phase system, because we know that most of the power system that we have for especially transmission systems are 3-phase systems. Therefore, we will take the case of a 3-phase system. We will start with the 3-phase line with equilateral spacing, because as we have seen for inductance calculation, we can always convert, if the line is transposed, we can always convert any system into an equivalent 3-phase equivalent equilateral spacing of the conductors by finding out the equivalent distance DEQ. So, here we have a equilateral spacing, conductor A, B and C, each with a distance d from each other. We also assume that this system consists of only 3 conductors. So, the sum of the total charges will be equal to 0, that is q A plus q B plus q C is equal to 0. Again, as earlier, we can find out the voltage between any two conductors. So, let us find out the voltage between A and B. So, VAB will be equal to, again using the same relationship that we have used earlier, it will be equal to 1 by twice pi epsilon into the Q2 charge on conductor A, Q A log n dBA by dAA. Due to charge QB, it will be plus QB log n dBB by dAB, that distance of conductor B to conductor B divided by distance of conductor B to conductor A, and due to charge QC log n dBC by dAC, that is distance from conductor C to conductor B and distance from conductor C to conductor A. Now, this, if we substitute the values of dB, dAB or dBA and dAA, dBB and so on, this can be written as VAB is equal to 1 by twice pi epsilon into QA log n d by r, dBA is equal to dAB, which is equal to d, and dAA is its self distance, that is r, the radius of the conductor, plus QB into log n dBB, again since the conductor radius we have assumed to be same, that is 3 conductors are of the same radius or diameter. Therefore, dBB is equal to r, dAB will be equal to d, plus QC log n dBC, which is equal to d, and dAC, which is equal to d. So, this is QC log n d by d, which will be QC log n 1. Therefore, this term will go to 0. Therefore, we have VAB is equal to 1 by twice pi epsilon into QA log n d by r plus QB log n r by d. Similarly, we can find out the voltage between conductor A and conductor C. So, VAC will be equal to 1 by twice pi epsilon into due to charge qa log n, the distance between A and C dCA, the distance between A to A, so dA, plus qB log n, distance of B to C, that is dCB, divided by d distance of B to A, so that is dAB, plus qC log n, distance of C to C divided by distance of C to A, that is equal to dCC by dCA. This will be equal to 1 by twice pi epsilon qa log n d by r, that is substituting the distances, d by r, plus qb log n d by d plus qc log n r by d. Again this term, since it is d by d log n 1, so this term goes to 0. So, we have VAC is equal to 1 by twice pi epsilon into qa log n d by r plus qc log n r by d. Now, if we look at these equilaterally spaced conductors, here the voltage VAB is equal to root 3 times VAN at an angle of plus 30 degrees from the x axis. So, this is equal to root 3 times VAN into root 3 by 2 plus j half. That is, we have converted this from polar coordinate to rectangular coordinate. Similarly, VAC. Now, VAC, if you see, is equal to minus of VCA, that is negative of VCA. This is equal to again root 3 times VAN, and this, if you see, VAC is at minus 30 degree from the x axis. So, root 3 VAN with an angle of minus 30 degrees. This is equal to root 3 VAN into root 3 by 2 minus j half. So, now if we add these two voltages VAB plus VAC, we get this as equal to 3 times VAN. That is, if we see, if we add these two, this j plus j half and minus j half will cancel out, and we have got 2 times root 3 by 2 into root 3 times VAN. So, that 2 will cancel out and root 3 into root 3 will give us 3. So, this will be equal to 3 VAN. Therefore, we will get VAN, that is voltage of phase A to the neutral, will be equal to 1/3 of the 1/3 of VAB plus VAC. So, substituting the values from VAB for VAB and VAC as we have calculated earlier, we will get this as 1/3 of 1 by twice pi epsilon into 2 times qa log n d by r plus qb plus qc log n r by d. That is, if we see here, VAC is qa log n d by r plus qc log n r by d, and VAB is 1 by twice pi epsilon qa log n d by r plus qb log n r by d. So, if we add, we will get twice qa log n d by r and qb log n r by d plus qc log n r by d. That is what we have got here. So, we have 2 times qa log n r by d plus qb plus qc log n r by d. So, from this relationship we can find out now VAN is equal to 1 by twice pi epsilon into, now QB plus QC is equal to minus QA, because q A plus q B plus q C is equal to 0. So, this becomes twice q A log n r d by r minus q A log n r by d, which can be put as plus q A log n r d by r, and therefore, we get 3 q A log n d by r, and this 3 will cancel with this 1 by 3. So, we have got 1 by twice pi epsilon q A log n d by r. So, once we have calculated the voltage between phase conductor A and the neutral, which is at 0 potential, then we have got CAN, or the voltage or the capacitance between conductor A and the neutral or the ground will be equal to q A by V A n, which comes out to be equal to twice pi epsilon divided by log n d by r farad per meter. This is line to neutral capacitance or line to ground capacitance. In general, we, instead of having d as we have seen earlier, we, if the conductor spacing are not equal, that is, we do not have a equilateral configuration of conductors, then other configurations can always be converted into an equivalent equilateral equivalent equilateral configuration, where the distance d is equal to d e q, that is the equivalent equilateral configuration distance. So, d e q is equal to cube root of d a b into d b c into d a c. This is what we had seen in earlier lecture on 3 phase line, that is in lesson 4. Now, let us take a more general case where we have considered a 3 phase bundle conductor line with unequal spacing. We have here a 3 phase line with 2 conductors in a bundle for each phase, and this configuration for the 3 phase system is a horizontal configuration. That is, distance from A to B, that is center of conductor bundle A to conductor bundle B is d a b. The distance between center of conductor bundle B and conductor bundle C is d b c, and distance from the center of the conductor bundle A to center of conductor bundle C is d a c. Whereas, each conductor has a radius r. Here we are assuming that all the conductors have the same radius, and the bundle distance, that is distance between the center of the 2 conductors, is d. As we had said earlier, this d is generally much larger than r. It is normally 10 times or more r. In general, we have around 30 centimeter or 40 centimeter distance between the conductors for bundle conductor lines. So, d can be of the order of 30 to 40 centimeters, whereas the conductor radius will be of the order of 2 to 3 centimeters. So, now again we need to find out the voltage difference between the 2 phase conductors. So, we find out VAB. Now, here what we have assumed is that conductor A is having a total charge of q A, and since we have a 2 conductor bundle, so each conductor or the subconductor in the bundle will be having a charge q by 2. So, it will be having q A by 2, this will be having q A by 2, this conductor will be having charge q B by 2, this will be having charge q B by 2, because all of them are of the same kind and same radius. So, C will be having charge q C by 2, this subconductor, and this subconductor will be having charge q C by 2. So, now in order to find out VAB, again what we need to do is find out the voltage between A and B due to the charges on each of these conductors or subconductors. So, VAB will be equal to 1 by twice pi epsilon. Now, due to charge on conductor subconductor 1 of phase A, it will be QA by 2, that is the charge on that subconductor, into log n dBA by dAA, that is the distance between A to B divided by distance of A to A, that will be again the radius of the conductor, plus QA by 2 due to the subconductor, the second subconductor in phase A, that is this conductor, this subconductor, it will be QA by 2 into log n dBA dash by dAA dash. Now, due to this subconductor, the voltage VAB will be given by QB by 2 log n dBB divided by dAB. Again, for the other subconductor of phase B, this will be plus QB by 2 log n dBB dash divided by dAB dash. Similarly, for the two subconductors, charge on the two subconductors of phase C, we will have components QC by 2 log n dBC by dAC plus QC by 2 log n dBC dash by dAC dash. This, after substituting the values, will be given by QA by 2 log n dAB by R, that is that AA, plus log n dAB by D, which is the distance dAA dash. Now, here what we are saying that dBA and dBA dash are almost same, because the distance between the two phase conductors is much larger compared to the distance between two subconductors of a bundle. So, this small approximation we have made, that is dAB is the distance between the center of the two conductors. So, this is QA by 2 log n dAB by R plus log n dAB by D. Similarly, for conductor B, or the charge due to conductor B, will be QB by 2 into log n R by dAB plus log n D by dAB, plus due to charge on conductor C, QC by 2 log n dBC by dAC plus log n dBC by dAC. Now, this, when we add these terms, finally can be written as 1 by twice pi epsilon QA log n dAB by RD, square root of RD, plus QB by log n square root of RD by dAB, plus QC log n dBC by dAC. Now, this, if we remember, the inductance relationship is very similar to that relationship, and therefore, this can be again written in terms of capacitance is equal to capacitance between neutral can be written as twice pi epsilon log n dEq by ds, where we have already defined dEq as cube root of dAB into dBc into dAC. Therefore, capacitance to neutral is given by the same relationship, except that we have now replaced R by ds, where ds is the effective radius of the bundle conductor and dEq is the equivalent equilateral spacing for the conductor. So, for two conductor bundle, as we had seen earlier, or in this case the ds is equal to, the self distance ds is equal to square root of R into D. For a 3 conductor bundle, the self distance ds is equal to cube root of R into D square, and for a 4 conductor bundle it is equal to 1.0491 fourth root of r d cube. This we had seen in the last lesson. Now, once we have calculated the capacitance, now we can find out the charging current, because there is a voltage and there is a capacitance between the conductor and the ground. So, there will be some current which will be flowing in the system, and this current which is flowing in the capacitance is called the charging current for the system. Now, this transmission line has a capacitance CAN for phase A, CBN for phase B, and CCN for phase C. Now, these capacitances we can find out the admittance. Admittance will be equal to twice pi f into C, that is, we will have y will be equal to minus j omega c. So, we can find out the admittance between the phase conductor and the neutral or the ground. So, if we are finding between two conductors x and y, so then we will find out the admittance for CXY as YXY, and the charging current will be YXY into VXY. This is equal to j omega CXY into VXY amperes. So, once we have calculated the charging current, we can also find out how much is the volt ampere reactive which is supplied by this charging capacitance of the transmission line. So, the capacitance of the transmission line will in fact be supplying reactive power to the system, and this will be given by QC, which is equal to Vxy square divided by Xc, or Yxy into V square xy, or Vxy square. So, we can find out the charging volt ampere reactive as omega Cxy into Vxy square. So, this will provide us the volt ampere reactive which is generated by the transmission line. And if we are looking for the charging current to the ground, then this will be equal to y into VAN. This will be equal to j omega CAN into the voltage between line and the neutral. So, once we know this current, we can find out by multiplying this by another V, that is j omega CAN into VLN square, will give us the reactive power generated by this line. So, for a single phase system, we have the charging reactive power supplied by the line given by y into VAN square. This is equal to omega CAN into VLN square volt ampere reactive. For a 3 phase system, this will be equal to 3 times the charging volt ampere reactive generated by a single phase line, or between each phase and neutral of the line. So, this will be equal to 3 times omega CAN into VLN square, which is equal to omega CAN into VLL square. That is, if we take line to line voltage or the system voltage for a 3 phase system, then the charging reactive power generated by the line will be given by omega CAN VLL square. Now, that we have seen how we can calculate the capacitance and also find out the charging current and the reactive power generated by the line, let us take one example to see how we calculate these quantities for a transmission system. So, this example we have a 3-phase 400 kV 50 hertz 350 kilometer overhead transmission line that has a flat horizontal spacing with 3 identical conductors. That is, we have 3 identical conductors placed in a flat horizontal spacing. The conductors have an outside diameter of 3.28 centimeter, that is, the diameter of the conductor is 3.28 centimeter, and the distance between the adjacent conductors is 12 meter. Now, for this system, determine the capacitive reactance to neutral in ohms per meter per phase and the capacitive reactance for the line in ohms per phase. So, for solving this, we will take case of a fully transposed 3-phase line. So, we have the fully transposed 3-phase line. The voltage is given by the relationship VAB is equal to 1 by twice pi epsilon, this is epsilon into QA into log n DEQ by R plus QB into log n R by DEQ, where DEQ is equal to D12 into D23 into D31 to the power 1 by 3, that is cube root of D12 D23 into D31. Now, substituting these values, we get this as equal to 12 meters into 12 meters into 24 meters, that is the distance between the conductor A and C. The cube root of this will give us equal to 15.119 meter. Similarly, we can write the relationship for VAC, and VAC will be equal to 1 by twice pi epsilon into QA into log n DEQ by R plus QC into log n R by DEQ. So, substituting again the values for the system, we have substituting the values, we will get VAB and VAC, and we know VAB plus VAC is equal to 3 VAN, and also we know that QB plus QC is equal to minus QA. Therefore, adding VAB and VAC, we will get VAN is equal to QA divided by twice pi epsilon log n DEQ by R. Therefore, the capacitance to neutral will be equal to QA by VAN, which will be equal to twice pi epsilon log n DEQ by R, and this will after substituting the value comes out to be 8.163 into 10 to the power minus 6 microfarad per meter, and we can find out the admittance, the charging admittance of the line to neutral, which will be equal to twice pi f into Cn. So, after substituting the value, we get this as equal to 2.565 into 10 to the power minus 9 Siemens per meter per phase. Now, we are given the length of the line as 350 kilometers. Therefore, Yn is equal to 8.978 into 10 to the power minus 4 Siemens per phase, that is multiplying this by 350 kilometer, which is 350 into 10 to the power 3 meters. So, this gives us this much, and the reactance will be equal to 1 by admittance, which comes out to be equal to 1.1138 into 10 to the power 3 ohms per phase, that is 1.1138 kilo ohms per phase. That is all for this lecture. We will continue with capacitance calculation in the next lesson, where we will talk about how we take into account the effect of earth for capacitance calculation. Thank you. Welcome to lesson 6 on power system analysis. In this lesson we are going to discuss transmission line capacitance, which we were discussing in lesson 5. We are continuing with it. Here what we will do is we will consider the effect of earth on transmission line capacitance. Actually, when we have these transmission lines, the phase conductors are in above the ground in overhead transmission system, and the distance between the phase conductors and the distance between phase conductor and ground are of the same magnitude, and therefore the earth, which acts as a equipotential surface, does affect the electric field lines and thereby the capacitance. So, we need to consider the effect of earth in calculating the capacitance for transmission lines. So, in this lesson we will discuss how the earth or the ground affects the capacitance of a single phase transmission line and how it affects the 3-phase transmission line. Then we will talk about a double circuit line, and we will talk about how we calculate the series and shunt impedance of the double circuit line. Such a system we are showing here. Here we have a 3-phase line. This is one circuit and this is another circuit which is placed here. So, this is a double circuit system. Here we are showing this double circuit line. This is one circuit, this is another circuit connecting 2 bus bars or 2 substations. Now, the current flowing in one circuit is IP1, the current flowing in the other circuit is IP2, where IP is basically a 3 element vector which consists of IA, IB and IC. So, we have IA1, IB1, IC1 of the circuit 1 and IA2, IB2, IC2 for the circuit 2. Now, this current flowing here from one circuit will be IP1 plus IP2, which gets divided into IP1, IP2, and maybe it is getting connected on this side. This is the system that we are showing. We have learnt about, we will do in lesson 7. Thank you.